Okay, so I had a good time putting this together. This is just a summary of some of the spacecraft that have visited Jupiter and some of the science that we've learned from it. Mostly radio stuff, but then I threw in some of the other discoveries that we've made. So Pioneer, Voyager, Ulysis, Galileo, Cassini, New Horizons, and future missions. We'll talk briefly about each of these. So here's some pictures, some of them artist concepts, but the launch date and then the encounter date for each of the missions. And then there's a bar timeline there to get an idea. So if you think about it, that's 2, 4, 6, only 8 spacecraft have visited Jupiter. And Juno is on its way. So a lot of firsts here for our Pioneer back in the early 70s. First mission to the outer planets. First vehicle and a trajectory to escape the solar system. First spacecraft beyond Mars, past Jupiter. First nuclear-powered spacecraft. And first human-made object beyond the outermost planet in the solar system.
Still going.
Still going, that's right. That's right. So, a couple of nice pictures from Pioneer 10 and Pioneer 11. So this is a sequence of images as it approached Jupiter and then past Jupiter. So crescent Jupiter, you don't see that from Earth. Never, right? You've got to be out there. So identified plasma, of course, first close-up images, charted radiation belts, magnetic fields. Jupiter is predominantly a liquid planet. And then, of course, studied magnetic fields, particle radiation, dust populations in the interplanetary space. And then that was Pioneer 10. Pioneer 11 took images of the Great Red Spot. Pioneer 11 flew high enough in latitude that it was able to get a polar view. So it made observations of the polar regions and made a calculation of the mass of the moon Callisto. And then Voyager launched in 77, and then each one flew by in 79, a few months apart. So there's the orbital trajectory of Voyager 1, Voyager 2. Arguably this may be a true statement. One of the greatest missions of discovery in history. And it's still going, right? What did they discover? Rings around Jupiter. Of course, the volcanism on Io. Very complicated atmospheric dynamics. Observed lightning. First measured the aurora. Discovered 3 new moons. And looked at the rotation of the red spot. And then beyond Jupiter, measured these shepherd moons in the Saturnian system. Found new moons of Uranus, Neptune, and found the moon Triton had activity on it, geyser activity. And as most of you know, that the Voyager 2 spacecraft was sent on this trajectory, so it used the flyby of Jupiter and Saturn to throw it out and fly by Uranus and Neptune. So the only one out that far to fly by both Uranus and Neptune. So the spacecraft itself, I won't go through all of this, but you guys seen most of this already. But here's the thermoelectric generators here. These are the antennas for the plasma wave antenna and also the radio antennas. There's a magnetometer out at the end of the boom. So there's a neat little graphic animation showing you the atmosphere of Jupiter. Isn't that amazing? You see those bands and belts, winds moving in different directions, and the rotation of the red spot. Quite incredible. So the radio science experiment on the Voyagers, this is really cool the way they do this. But so it was able to measure the properties of the planet and some of its satellites just by making measurements of the communication, the radio communication back and forth between Earth and the spacecraft. Right? You can measure Doppler shifts and accurately track the motion of the spacecraft to make those kinds of measurements, and also look at determine masses. Look at the gravity field of Jupiter. Again, all just based on the radio communications between the spacecraft and the ground. So in terms of the radio science, so the planetary radio astronomy experiment was a sweep frequency receiver from 20 kilohertz to 40.5 megahertz in both polarizations, and the 10-meter orthogonal 10-meter monopole antennas were used were the antennas for the receiver. And then there was also a plasma wave instrument on there to look at the plasma concentrations and plasma profiles. And that was a 16-channel receiver from 10 kilohertz to 56 kilohertz. Sorry, 10 hertz to 56 kilohertz. You guys remember this image not too long ago? I thought that was neat. So that's the Voyager 1 signal from the VLBI. And of course, that's some of the famous images of the volcanism on Io, on the Voyager spacecraft. There's a little animation of some of the plumes coming up around the limb. That was I think one of the most important discoveries, I believe, for the mission. And you've seen this plot before. So this is the radio receiver from. There's a low band and a high band receiver from 20 kilohertz to 40 megahertz. So beautifully was able to detect the decametric and then some of the other lower frequencies, the hectometer emission, radio emissions, and the kilometer emissions as well. And it gave us the good model of the magnetosphere as it flew through there, so you can then model what the magnetosphere looks like, get the electron densities in and around Io and the torus, detected these high energy, the trapped particles. I mean, we knew that the radiation belts existed there, but was able to make measurements there. And this is kind of interesting. It determined that the magnetotail extended out 5 AU. So from Jupiter all the way to Saturn. From the magnetospheric influence is that's the extent of the tail. And of course, it was able to. Voyager, we were able to map out in some ways where the decametric, hectometer, and kilometric radio sources are located. And then Ulysis in 1992. It was, of course, the primary mission was to observe the sun and fly around the poles of the sun a couple of times, but it needed Jupiter's gravitational influence to do that, so it flew up high latitudes and then has gone around, I think twice. So there's actually 2 encounters with Jupiter there, but unfortunately the radio experiments only went up to 940 kilohertz, so just below 1 megahertz, so not any decameter results there, but a lot of interesting results in the hectometer band. Using the spin of the spacecraft and the antennas there, I've forgotten how many antennas there. I know there's at least 2 here. I don't remember if there's there
should be a
3. Was there 3 orthogonal?
Just thinking.
Okay. Anyway, they were able to use
one in the steep plane and one in the axis.
Okay, so orthogonal set of antennas, but they were able to use the spin of the spacecraft and do direction finding, so to find out what direction the radio waves are coming from. So they were able to almost pinpoint, in some cases, where some of the hectometer radio emissions were coming from. And they got a high latitude look at some of these sources, so that was pretty interesting. And it spent 12 days through in the magnetosphere of Jupiter, flew through the plasma torus and measured the electron density. The longitudinal asymmetries of the torus, so some of you asked me about that. Is the torus uniform? So no, you've got lots of different structures going on there. It was able to map some of these, or detect some of these moving electrons. So looking at how the current path was sort of connected via the plasma sheet and the ionosphere. So that's the, oh, sorry about that, the radio burst. So that's the radio burst in the dawn and the dusk sector at high magnetic latitudes. Look at the direction of the magnetic field in the evening sector of the planet, which allows you to look at how the plasma is flowing in the tail. And this is the direction finding experiment to map the hectometer sources. Discovered these narrowband kilometric radiation, so not to be confused with decameter N events. So these are completely different. These guys are coming from the outer regions of the Io torus. And then there's these weird, they call them Jovian type 3s, so they look like type 3 radio bursts in the spectrum, but they're coming from Jupiter. Very rapid drift in frequency. So that was Ulysis. There's an example spectrogram from Ulysis showing you some of the hectometer emissions here, and then lower frequency kilometric radio emissions, and then way down here you're looking at the plasma, the various plasma waves, and sometimes you can see what am I thinking of here, where you've got resonances here, so certain frequencies, and then you see a resonant band of emission and another resonant band of emission, so lots of detail in this flyby spectrum. And then Galileo launched in 95? I can't remember now. Launch, oh wow, what am I, way off, sorry about that, 89. And then arrived in 95. So it's very complicated orbit to get to Jupiter. It flew by Earth, took a beautiful picture of the Earth-Moon system, and then flew by Venus and took some nice pictures of Venus. Then it flew by a couple of asteroids. Got some nice pictures of the asteroids. Oh, there's the Venus picture there. And then on out, and then made its encounter with Jupiter, and orbited Jupiter for 7 years or so. 8 years, I guess. Orbited Jupiter, I think actually it was more than 34 before they turned the thing off, or they altered the orbit to end the mission. And in doing so, it flew by, made many flybys of the moons to make, direct measurements of the plasma around these moons. Of course, imaging the moons. So a lot of great science came out of the Galileo mission. So discovered ammonia clouds, confirmed the volcanic activity on Io. Gave evidence supporting that Europa has a subsurface ocean. Discovered a magnetic field around the moon Ganymede. And also gave evidence suggesting that the other Galilean moons had a subsurface liquid ocean. And studied the rings and the formation process by dust from the interplanetary meteoroids as the source of some of that dust. Made observations of the outer rings of Jupiter and looked at the global dynamics of the atmosphere. And this is a neat spectrogram showing the log plot of the frequencies. Galileo, the top end for the Galileo radio experiment was 5.6 megahertz. That's right in the lower region, right the lower end of the decametric, we call the decametric band of the spectrum. So we couldn't make we made some simultaneous observations of the ground, but there's no overlap frequency coverage from ground-based emissions. But here you can see the Jovian radio emissions up here, so above a megahertz. That's some hectometric and some decametric in there. And then below you see plasma emissions, and this is actually showing you the closest approach where the spacecraft flew by close enough by Ganymede, and you're seeing the plasma emission raise up here and then drop down. So that's flying through Ganymede's magnetosphere. Isn't that neat? So you got these different bursts, chorus, broadband burst, and then this upper hybrid frequency there. That's a way of determining the electron density. And Cassini flew by Jupiter in 2000, December of 2000, right around New Year, even into January 2001. And again, another complicated sort of orbit, but needed Jupiter to swing its way out to Saturn, and it's still going. Are you part of one of the Cassini experiments? You're part of the team, right? Yeah, okay, that's what I thought. And that's a Cassini image, beautiful image of Jupiter. Baptiste showed this one a little bit smaller, but there's the spectra. The high frequency end of its radio receiver was about 16 megahertz. So pretty good. And we made some comparisons with some ground-based data, but hard to see there. But there's some IO emissions and non-IO emissions. You can see some arc structure in there. And then lower frequencies, this is the narrowband kilometric stuff from the IO plasma torus, and broadband kilometric emissions, the hectometric emissions, and then these much lower frequencies, these quasi-periodic bursts, QP bursts they're called. So a very complicated spectrum there, but really nice data from Cassini as it flew by Jupiter. And then recently, or semi-recently, we had the New Horizons spacecraft fly by Jupiter on its trajectory to Pluto. And there's a nice image of Io at night, or in Jupiter's shadow, and you can see the hot spots from the volcanoes there. That's pretty amazing. And here's the orbit. This is the flyby of New Horizons past Jupiter, so it didn't get too close. But it did look at some atmospheric structure. It searched for some new moons. It did not find anything. And it looked at the ring composition and made some magnetospheric measurements as well. It did fly down the tail, so made some pictures of heat-induced lightning strikes in the polar region. The little red spot, you remember that when it sort of came around? And it's still around, I think, growing, while the great red spot, I think, is shrinking. So it took pictures of the faint ring system. There's an aurora picture from New Horizons. And measured some of these bubbles of plasma in the magnetotail. And so we think that there's some, I think the plasma guys know how these plasma bubbles basically kind of diffuse out and down the tail. So it was able to fly through the tail for an extended period of time and make some measurements on how that plasma moves. And then soon we're going to have Juno, and that's going to be a pretty exciting mission. As Jen mentioned earlier about the orbit of the spacecraft will be polar, so that's going to give us some really fantastic views of some of the radio sources. But Juno is named after the Roman goddess who could pierce through the clouds. So she's unveiling Jupiter underneath the clouds. So it should arrive in 2016, but I don't know when they're going to start making radio measurements, certainly before closest approach for the first orbit. So maybe even late 2015 we might start getting some Juno data. Three little figurines that are on the spacecraft itself. There's Jupiter, Juno, and Galileo. There's the spacecraft. This one is not nuclear powered, so that's sort of an interesting power source there. So it does have a dipole, and it does take, will make radio measurements up to 40 megahertz. But as I just found out from Baptiste, it may not have, it doesn't have polarization capability, and it does not have a way to do direction finding. So we'll take what we can get. So this is some of the questions it hopes to answer. So it's really going to look at the formation and the interior structure of the planet, and hopes to make better models for really the solar system formation, because there's planetary formation is a kind of a conundrum, how the planets form. Which came first, the large planets, the small planets, and what is the mechanism by which, and the time scale on which these things form. So hopefully it will help us answer these questions. The inside structure, it will use gravitational measurements from the orbit to map the gravity field and look at the interior structure. How the atmospheric features might be tied to the deep interior. And then this one is going to be really interesting. what are the physical processes that power the aurora? So because it's a polar orbiter, it's going to be looking right down on those polar caps and going to be making some incredible measurements of the aurora, I think, and of course what the poles look like. Okay, that's it. Quick tour. Recent spacecraft that visited Jupiter. That's all. Well, thank you very much. I'll take a question if you have any.
I have to ask this.
Yeah.
Did any spacecraft find a large black monolith in your eye?
There were some black things on Europa, I think, but they turned out to be cracks in the ice, as far as I know.
About Juno, so as you said, I would say that the radio receiver, I will be nasty. The radio receiver, the other is like the radio Jove. It will be not very directive and it will.
Yeah, so it's a basic dipole antenna, you're saying.
And actually those solar panels.
And what?
The solar panels, the system is switching them back and forth all the time.
Oh.
We will have switch for stuff like this.
Okay, okay.
So
we shouldn't get our hopes up too much. Okay. As I said, we'll take what we can get, I guess. Yeah.
I have a question. How do they measure the plasma waves? We were talking about the spacecraft flying through is that a radio type instrument?
Well, there are low frequency, receivers that would measure some radio emissions generated by plasma. But then they have particle detectors as well. So it's a separate experiment that actually measures the particle content as it's flying through the plasma.
So those plasma waves, they're density waves then, and they're actually performing a count per centimeter as the spacecraft flies through the plasma?
I don't know that for a fact. I don't know how it's making that measurement.
That can be. So they have the particle detector, particle flies through, makes an electrical signal, and they can detect. So the particle, the distribution of particles is always aligned with the magnetic field. Because all particles are rotating around the magnetic field. So they are scanning for various pitch angles, as you
Okay, yeah.
So all those are scanning.
Scanning for what?
For the
Actual particles,
Okay.
electrons and
the
protons,
velocity of particles depending on that pitch angle.
or even electrons, protons, or even ions, heavier nuclei that are out there. Okay, I guess we'll last go around. We ready? Yeah. Okay. So the last go around here.